this is going to be kind of a breathe easy day, right? This is all material you've seen before. There's no calculus today. This is a review of exponential functions. And the purpose of reviewing it today is that next class, we're going to derive the formulas and use the formulas for finding the derivative of exponential functions. Okay, so suppose an air freshener starts with 30 grams and it evaporates. So I'm going to write a formula for the quantity, Q grams of air freshener remaining T days after the start if the air freshener decreases by 2 grams per day. Okay, so somebody help me write a formula, Q in terms of T, if you start with 30 grams and lose 2 grams per day.
30 minus 2.
You got it. So Q, the quantity, start with 30, subtract 2 grams each day for T days. What kind of function is that? Linear. Good. All right. Slightly different. We're going to now start at 30 grams, but we're going to decrease by 12% each day. Okay, so now I'm going to write Q equals, I'm starting with 30 again. How do I represent a decrease by 12%? $30 times 0.12 T, but that's how much I lose, right? How much is, I'm trying to model how much remains, right? 0.88 is how much remains, right? So if I multiply by 0.88, that's how much remains. If I lose 12%, 88% is staying. And that's how much that's what I'm trying to model, how much remains after T days. So it's 0.88 each day, so I have to multiply by 0.88 over and over and over again. How do we represent repeated multiplication? An exponent, yeah. So the T goes in the exponent on this one. So that is what we call an exponential function. Exponential functions are of the form P of T is P naught times a to the T, where P naught is your initial quantity and a is your base. So in our example up here, our initial quantity was 30. 0.88 is our base. Okay. We're going to insist that a be positive and a not be 1, right? If a were negative, then the sign of Q could be positive and negative depending on the value of T, right? After 2 days, you'd have a positive amount. After 3 days, you'd have a negative amount because cubing a negative number would give you a negative. So we have to say a has to be positive, and a can't be 1 because if a were 1, nothing would ever change, right? 1 to anything is still 1. Okay, so if a is bigger than 1, a is bigger than 1, we have exponential growth, yes. Or if a is between 0 and 1, like in our example with the air freshener, we have exponential decay. All right, instead of writing P naught equals P naught times a to the T, which uses base A, sometimes instead we use base E. So instead of writing P naught a to the T, we would write P naught times e to the KT. Those are completely equivalent expressions. Okay, meaning they tell you all the exact same information. Any function that you can write as P naught times a to the T, you could convert it to P naught e to the KT and vice versa. Okay, when you use the E, the one that has E in it, whenever you see the phrase continuous growth or decay is referring to the equation with the E in it. Okay. So if we're dealing with continuous growth or decay, if K is positive, we have exponential growth. And if K is negative, we have exponential decay. E is an irrational number. It's approximately equal to 2.718. And its derivation, where that number comes from, will be done in the group activities. So you'll get to see that in a minute. Okay, so I would like to figure out the continuous decay rate that corresponds to the 12% daily decay rate from question 1B. Right, so we had a 12% decay rate up here for the air freshener. So my function was Q is 30 times 0.88 to the t. And I would like to write it as q equals 30 because p naught is the same in either case, e to the k t. Just going to figure out what k is. So for these two functions to be equivalent, it would have to be that they equal each other. 30 times 0.88 to the t would have to equal 30 e to the kt. All right, so the 30s kind of don't matter. It's the same on both sides. If you divide both sides by 30, they go away. So 0.88 to the t has to equal e to the kt. All right, I'm going to rewrite e to the kt in just a little bit of a fancy way. So this is e to the k to the t. Do you agree that those are equivalent? Yeah, because when you raise a power to a power, you multiply the exponents. All right, so for this and this to be the same, it's got to be that 0.88 equals e to the k. So 0.88 has to equal e to the k. How do you figure out what k is? Yeah, so that's tough though, because in order to take a certain root, you have to know what root it is, right? Like if you're going to tell your calculator to take a root of 0.88, you have to give it an actual number. So what do you, it's the natural log. Yeah, it's the natural log of both sides. So if we take the ln of 0.88 and the ln of e to the k, this is like your go-to tool whenever the variable is in the exponent. So yeah, what is the ln of e to the k? Just k, yeah. The ln of e to the k is k. That's the definition of the ln. It's the inverse of the exponential function. So it undoes whatever the exponential function did, so it brings the k back. And the ln of 0.88 was, is that what you were reading to me? And I'm sure that that's approximate. Oh, 0.128. Okay, does it make sense that that number came out negative? Yeah, because it's decay, so we expected k to be negative. We knew it was decay because my base was smaller than 1 when it was in the daily decay. So this is the continuous decay rate for 12% daily decay rate. Sorry, what? Yeah. So what did we end up doing? We ended up taking the ln of the, yeah, you can just take the ln of a, and that will give you your continuous decay rate. But I can't just give you the rule, right? Because then it seems like magic, and it's not. Question? Where did I get the 0.88? So okay, I'll go all the way back up to up here where I wrote the equation. So I'm decaying by 12% a day, right? You're losing 12% a day. So if you lose 12%, how much do you keep? You keep 88%. That's fine. So every day I take 88% of how much I have. And so you multiply how much you start with by 0.88. And then you do that over and over and over again each day.
You're 1 minus r.
1 minus r, yeah. If it's decay, so this is your r, this is your decay rate. Yeah.
1 plus r.
Sure, yeah, you can think of it that way. Yep. Yeah, because if it's decay, you're going to subtract it from 1, but if it's growth, you add it to 1. Because if you were growing by 12% a day, you would multiply by 1.12 because you get to keep 100% of what you had plus 12% more. Okay, so we're going to sketch some generic exponential growth and decay curves, p naught times a to the t. So let's see, we'll do growth and decay. Okay, who remembers what an exponential growth curve looks like? Yep. So it's something like that, right? And this value, what is that? That's p naught. Yeah, it's the initial value. P naught. Because if you make the t a 0, if t is 0, anything to the 0 is 1. P naught times 1 is p naught. So your y-intercept is always going to be p naught. And then exponential decay. What's that look like? The opposite how?
It goes down.
As time goes to infinity, it approaches 0. So it looks kind of like this. And this is also P naught. So those are super generic growth and decay pictures. And you're going to use those pictures in the first activity to answer fill in some blanks about properties of exponential functions.